Good morning to one and all. I am Dhanashekhar, Assistant Professor, Department of CSE, Shriram Engineering College. Today we discuss about Euler and Hamiltonian graph. This concept are used in many real-world applications such as network routing, GPS, and electrical circuit designs. The topic helps us to understand how we travel through a graph by visiting every edge exactly once. Next one, Euler graph. A connected graph is called an Euler graph if it contains an Euler circuit. An Euler circuit means every edge is visited exactly once. The starting vertex and ending vertex are same. A graph is called Euler graph if it contains an Euler circuit. An Euler circuit means we can start from a vertex, travel through every edge exactly once, and return back to the same starting vertex. The important idea is every edge must be used only one time. We must end at same vertex where we started. This concept was introduced by the mathematician Euler. Consider take this example. This is an example for 7-bridge example. The vertices are indicating by the land area. The edges are indicated by the bridges. Next, for example, for Euler path. Let us see a simple example. We have a 4 vertex A, B, C, D. The edges connected them, forming a square circle. Now let us check the degree of each vertex. The degree of vertex A is a 2 and vertex B is also 2, C is also 2 and D is also 2. All the vertex are same degree and also even degree. Therefore, this graph, that means the right side of the graph is a Euler graph. This graph contains Euler circuit start from vertex A to B and B to C and C to D and last D to A, so to form one circuit. So here every edge is visited exactly once and we return to starting vertex A. On left side of the graph is not a Euler path. There is no direct edges from A to B or A to D and D to C and C to D. Next, move to next slide. Euler circuit. An Euler path is similar to an Euler circuit. The difference between the starting vertex and the ending vertex are different. So we travel through every edge only once, but we do not return the same starting point. A graph that contains Euler path is called as semi-Euler graph. So consider this example. Take this left side example. This example to contain Euler circuit not possible. The reason is we start with vertex A to B and B to C and C to D, but we cannot reverse D to C. So this is not a Euler circuit. To consider the right side of the graph, we start from the vertex A to B and B to C and D to C and C to D. and D to B and B to E and E to A. So here to form circle like this. So this is the Euler circuit and also called Euler. There is a path from vertex A to again last the same vertex A. Next one, the properties of Euler graph. For the graph to be an Euler graph, it must satisfy certain properties. First, the graph must be connected. This means every vertex should be reachable. Second one, all the vertex must have even degree. Third one, the graph must contain an Euler circuit. And last, the number of vertex with odd degree must be 0. If all the conditions are satisfied, the given graph will be a Euler graph. Then next one, the types related to Euler graph. The first one, Euler graph. All the vertices are even degree. There is a Euler circuits in Euler graph. The second one the second is a semi-Euler graph where exactly two vertices have odd degree and an Euler path exists. And third one, non-Euler graph where more than two vertices have odd degree. In this case, neither Euler path nor Euler circuit exist. And next slide is a necessary and sufficient condition for Euler graph. The is a main necessary and sufficient condition. A connected graph G is an Euler graph if and only if every vertex of the graph has even degree. This is a necessary and sufficient condition of Euler graph. So consider this example. We have a 4 vertex and each vertex have a even degree. The vertex A contains degree of 2 and vertex B have a 2 degree and vertex C and D have a 2 degree for each. So this graph to contain Euler circuits, this graph is also called Euler graph. This graph to satisfying this condition, every vertex of graph must have even degree. And next graph, semi-Euler graph. A common example of semi-Euler graph is a house-shaping graph. It looks like a square with triangle on top. In this graph, two vertices have odd degree, another vertex have even degree. Another vertex have even degree. Because of this, the graph has Euler path but not an Euler circuit. So we can start at one odd vertex and finish at another odd vertex. So consider this is example, the house plan, the one triangle on top of the square. We start from this vertex A that contains degree of 2 and vertex B contain degree 3 and vertex C contain degree 3 and the remaining vertex D and E have two vertices. As per the theorem, the two vertices are odd degrees. The other vertices are even degree. So we can start from travel A to B and B to C and B to D and D to E, E to C and C to B. Necessary and sufficient conditions for Euler graph. A connected multigraph has an Euler circuit if and only if each of its vertices has even degree. And second condition, a connected multigraph has a Euler path but not an Euler circuit if and only if it has exactly two vertices of odd degree. Here a simple trick to identify the graph type, just count the number of odd degree vertices. If the graph has 0, there is no odd vertex, it is an Euler graph. If the graph has two odd vertices, it is a semi-Euler graph. If the graph has more than two odd vertices, it is a non-Euler graph. This method to help quickly identify the graph type during your exams. Thank you.